Hello everyone, my name is Shailesh Saraykar. I am head of process safety at Engineer Inc. And today I'll talk about need for re-evaluation of relief system design under current new normal as certain credits disappear. Let's talk about equipment overpressure. Overpressure is excess buildup of material or energy or both within a system, and it's prevented by relieving fluid from overpressurized equipment or equipment system. There are various overpressure scenarios which can cause overpressure, and these are listed in API standard 521. So some of these overpressure scenarios are listed here. Overpressure can lead to a major incident if protection is not in place, not functional, or not adequate. There are multiple ways of protection from overpressure. Best is inherently safer design, but it can get expensive. So let's say, for example, if pump is feeding into a system and then the maximum discharge pressure of the pump is 500 psig, then the entire downstream system can be designed for 500 psig. So there are no applicable overpressure scenarios for that downstream system. However, it can often result in over design, and as I said earlier, that can mean additional cost or excessive cost for the project. Most commonly seen is installation of pressure relief devices. Then there's prevention through safety instrumented solution, where installation of relief devices is impractical. And this is also expensive solution, as the safety instrumented solution, it has to be seal integrity level or seal level of 2 or 3. Then there's prevention through operator intervention or administrative controls, which is going to be the focus of our discussion today. Let's look at layers of protection. So there's basic process control system. API does not allow credit for positive action of instrumentation in relief system design. Then there is prevention through operator intervention or emergency shutdown or physical devices. And then eventually mitigation after incident has happened. But best is prevention. Now, due to current pandemic situation worldwide, numerous measures have been taken by multiple companies as a part of the emergency response plan. So some companies have lower production because of the lower consumption. Some companies have reduced staff to cut down the cost. And then some companies have adopted policies where they are allowing only essential to operation persons on site or personnel on site, which has resulted in limited availability of on-site production staff. So how does this impact relief system design or overpressure protection? So I'll explain that in next few slides. So let's look at one of the scenarios which needs to be considered for API standard 521, which is overfilling. So here I have shown a system where there is a pump which is capable of developing a deadhead pressure of 500 psig, and it's feeding into a system which has MAWP of 300 psig, or this vessel has MAWP of 300 psig. So if this valve is blocked, the system will fill up with liquid, and since the pump discharge pressure exceeds the MAWP, this can result in overpressure. So one way to mitigate is installation of relief device on the vessel. Now, API standard 521 states that credit for operator intervention can be taken, provided the listed criteria here is met. So there is an independent high-level alarm installed on the system. This alarm should be independent of the initiating event. Operator should have adequate response time, which is considered to be 10 to 30 minutes. There shouldn't be any alarm overload on operators. Operating procedures should be in place. They should be readily available to the operators, and then the operator should be trained in these procedures. Now, with the limited staff, there might be possibility of alarm overload on operators where they might not be able to take effective action to make sure that scenario does not happen. Also, operating procedures. I mean, is there enough staff to maintain these operating procedures, rewrite them, or even train the operators in those operating procedures? Are these training documented? If this is not happening, then the overfilling scenario needs to be relooked at. And how dangerous can be overfilling scenario? So this is an industry incident which happened in 2005 in Texas City refinery, where isomerization tower overfilled during startup. It clearly was alarm overload situation, and this liquid hydrocarbon found the outlet and source of ignition, resulting in explosion. So this explosion killed 15 personnel and 170 were injured. Another overpressure scenario where credit for operating procedures is allowed by API is thermal expansion. So here I have shown one exchanger. This is the hot side of the exchanger, and then this one shown in blue is cold side. So cold side has block valves. It's a typical configuration. And this cold side can be blocked in when a hot side is flowing. So this can result in overpressure due to thermal expansion. Now, one way to mitigate this overpressure contingency is to install a thermal relief device on the exchanger. Some operating companies take credit for operating procedure per API standard. So what API standard says, API standard 521, it states that operating procedures, if they are in place to isolate and drain hot side before the cold side is isolated, and operators are trained in these procedures and signs are posted in the field, then credit for this procedure can be taken to overrule thermal expansion scenario as a credible scenario. However, with the current situation, same question as previous, are these operating procedures being followed? How closely they'll be followed with current limited staffing? Are operators being trained? Is there enough staff to do that training, or it's only limited to essential to operations person operating the plant? And are signs still posted? If again any of this is not happening, then then thermal expansion scenario has to be re-evaluated. Now, again, same as previous, how bad this thermal expansion can be. So this is industry incident again, which happened in 2013. So this was in olefins plant, propylene fractionator, reboiler associated with propylene fractionator. So this happened during startup, where cold side was isolated for a good amount of time, and then the liquid from the cold side started accumulating because of the leakage. Then during startup, while the cold side was still isolated, hot side valves were opened, and then the hot side fluid came into the exchanger. It imparted heat to the residing liquid on the cold side of the exchanger, which caused vaporization. These vapors were trapped as the block valves were closed. Again, lapse of procedure or lack of operating procedure. And this resulted in tremendous amount of overpressure, blowing up this equipment, which killed 2 people and then 114 were injured. Check valve failure is another overpressure scenario where credit for inspection program is allowed to reduce the backflow significantly. So here I have shown one example where there is a feed surge drum, a pump feeding into the reactor system, and then there is this check valve V1. Now what API says is, if multiple check valves are installed in a system, so like in this system, if let's assume there is check valve V1 and check valve V2, and these are inspected and maintained, then reduction in backflow, a significant credit can be taken for reduction in backflow, which is about 90%. So that's pretty steep. So in this situation, if pump fails and check valve leaks or fails, then the reactor material will flow into the feed surge drum. However, if I have multiple check valves here, which are inspected and maintained, then I get a significant credit for that. Now, with the current situation, there's question about how closely this inspection will be done, how closely this procedure will be followed, and are these valves really maintained? So inspection and maintenance program is at question with reduced staffing. And if credit for multiple check valves was taken in the original design, which is no more available, then this scenario needs to be re-evaluated and re-looked at. So those were some examples. Here I have presented few more examples, which few overpressure scenarios which can be impacted because of some of the measures which have been taken into account to address the current pandemic situation, reduce staffing. So control valve bypass opening is a scenario which needs to be considered per API standard 521. Our observation is most of the control valve bypasses are gate type, especially in old designs like 1960, 1970. So opening of this bypass valve can result in a tremendous amount of flow rate going to the downstream system. And if upstream pressure exceeds the downstream MAWP, then the relief devices are typically found to be undersized on the downstream system. And one way to mitigate is to car seal close the bypass valve or put a restriction orifice in place. If the bypass valve is car seal closed, then that bypass valve has to make it on the car seal list, which is maintained. Or if restriction orifice is put in place, then that restriction orifice has to be on safety critical list. Inadvertent valve opening is addressed through car seal closure of that valve, provided hydrotest pressure is not exceeded. Fireproof insulation is provided for some of equipment where relief devices are undersized for fire. So providing fireproof insulation reduces relief requirements significantly. But that fireproof insulation has to be on safety critical list. Then the blocked outlet, to get rid of the blocked outlet situation, some of the block valves are car sealed open, provided hydrotest pressure does not exceed. But again, those block valves need to be on the car seal list. Then depressuring procedures are adopted to avoid overpressure due to fire, provided there is a relief device elsewhere in the system. Now, so these scenarios, overpressure scenarios, are addressed either through procedure or developing administrative controls or through some safe maintenance of safety critical list. However, if this is going to be impacted again by reduced staffing or some other factors which will allow or which will impact following these procedures or maintenance of these lists, then all these overpressure scenarios have to be evaluated. Now, some plants are operating at a lower throughput because of the lower production. So if production rate is decreased, that can also have some impact on performance of the relief valves. So this can actually result in relief devices being oversized. And if relief devices are oversized, there's not enough expansive force to keep them open during overpressure scenario. So what will happen is relief device will open, relieve the material, and because of lower rate in the plant, there is not enough expansive force to keep the relief device open, so it will tend to close. So there's, again, as the pressure builds, it will tend to open. So there is this opening and closing of the relief valve, which if becomes high frequency can cause some damage and compromise the safety protection. Now, relooking at some of these contingencies or overpressure scenarios, if can change the sizing basis for the knockout drum. As now, as we looked at overfilling, so it's possible that another case becomes controlling for sizing of the knockout drum. And if knockout drum is not adequately sized for that contingency, then it can result in liquid carryover via flare. So these are some overpressure scenarios that need to be relooked at. I can cover only so much in 30 minutes or 15 minutes, but the bottom line is, to conclude this presentation, measures have been taken by multiple operating companies during this pandemic. These measures can have negative impact on the process safety, as we have seen through some examples. And overpressure scenarios should be evaluated, especially where credit for operator intervention, operating procedures, or administrative controls have been taken in the original design. So with that, I conclude my presentation. Thanks a lot for your time.